Welcome back for part two of lecture three, where we are dealing with two electrons. So we are really working with Hartree-Fock, and what we have done is to use a variational principle to solve the Schrödinger equation. Essentially, instead of solving the Schrödinger equation, we minimize the total energy uh, for by variation of the wave function. So we have trial wave function. It's what we've done on the first part. Try to find the lowest energy. And so the idea I gave you an example of that to have a variational parameter. It was called alpha for the exponential of the for the coefficient of the exponential. uh, we try to have variational parameters and we minimize the trial orbitals until we find the right answer, right? Um, so we know that whatever energy we have, it's always an upper bound of what the right answer is. Um, so you could come up with all sort of ideas here. You could come up with function with lots of parameters, uh, even an infinite number of functions, um, and you could try that, and then hopefully get a better and better numerical solution to your problem. This is totally possible, and it's actually quite fun to do. Um, I do remember that decades ago we were able to do this on the computer, so I can imagine now that it would go super fast on a laptop. And so this is maybe kind of interesting to do that, to minimize the functional for a series of function that you can use until you get a better and better picture of the problem. Now, I would like to say something about a word that's on this slide here. We increase the kinetic energy. So this is something that we see a lot, and I would really love for you, the listener, to get a sense of this more and more. All those little intuitive ideas that I try to give to you. We usually, when we do this and we add more and more functions, uh, could be all sort of different functions. We usually do this in order of increasing kinetic energy. What does that mean? That means that the expectation value of those functions that we add have a larger and larger kinetic energy. That's what it means. But the reason why we do this is because the larger the kinetic energy, the more localized the wave function is. So that means that usually the behavior that's harder and harder to capture in the solutions are the solutions that are close to the nuclei. And so in order to localize more and more those trial wave function, we go do them with increasing kinetic energy. Now, let's try to talk about an alternative to this variational principle. And that's what I'm going to talk to you in this second part of lecture three. Uh, the alternative, of course, is to use functional calculus, right? And so we are going to do that for two electrons. So my total energy can be written as this. So I'd like to explain to you a little bit where I got this from. And this energy does not include the constraint on the number of electrons, right? I wrote E, not F. That's just, don't worry too much about this. It's just to explain, because what I want to focus on those terms. So it's twice the kinetic energy of a single particle. That's why there is a 2. So we calculate this for a single particle. And it is twice the external, the interaction, the potential, the energy with the external potential. And finally, this is the interaction that you have between electrons. That's given there, U phi divided by 2. So we have a divided by 2 because, of course, if an electron interacts with an electron, the electron interacts with the first electron too. And we do not want to count twice. The half that we have in the potential comes from the fact that the energy, so which is the functional derivative, is actually the 1/2 is going to go away, and so therefore we go back to Coulomb-like potential. So this is what we have. Now, here for this particular U value, I use the delta Dirac that I used in the previous part of lecture 3. But if you wanted to do this completely, you would need to use something like I have in the blue box on the top. So you would have to use the actual Coulombic potential. Okay. So we have the one electron functional is, and U is the Hartree energy. So the Hartree energy will be given by the value up there. And this is only true because this term is only true because we are using independent particle wave function. So the wave function, which is the product of the two wave function. So that's only true for that. And so for the two electrons in Hartree-Fock, again, with the product of the wave function of an independent particle, we find that the electron-electron interaction is going to be equal to 2u over 2. Okay? So this is going to be for the potential. So now, if we can minimize this functional of the orbital, subject to the restriction is normalized, we can find the right answer. So let me show that to you now. We can actually do this. We start from this problem that we want to minimize. How do we minimize this? And so, by the way, sorry, before I answer the question to how we minimize this, each of those terms are single orbital component. It's just because in Hartree-Fock, we are essentially considering the problem to be non-correlated, and we have just a correction, which is the Hartree potential. But these elements there are single wave function quantities, and this is why we use those value of twos and so on and so forth. Those two, because each electron basically contribute the same amount of energy, that kind of thing. So we can calculate this by using the variational principle, and this is what we've done already last week in lecture 2. The difference now is that we add a little term here, which is the Hartree potential. And the Hartree potential comes from now the fact that the electron is actually interacting with the density of the other electron, right? This is what we obtain in Hartree-Fock. It's very nice. So the Hartree potential is actually given by this. Is the it is indeed the variation, the derivative, if you will, of the energy, right? The potential is always obtained by the gradient of the energy. This is what we obtain here, and it turns out in our very simple problem of Dirac delta that Hartree potential is just a density, right? So this is quite interesting because now we have something that we can try to solve. Okay, good. Now, I'd like to make a number of comments. The factor of 2 that divides the Hartree potential is due to the exchange effect. So we basically, an electron cannot interact with itself. This is basically what it means, right? So if we consider an electron interacting with another one, we already took into account the other electron interacting with the first one. So we do not want to double count. Now, you probably have noticed that and I'm going to go back one slide, and I'm going to go to the last row here. If I substitute VH in this equation, I see that the equation itself between the curly brackets depend on the density. But the density itself, you don't know it until you know the solution, because the density is phi x psi square, right? Square modulus of psi. So that's a little bit of a problem because you need the solution to know the problem. And so the way it's done in practice, and we are going to talk about that quite a bit, and it's going to come back in DFT a lot, is the fact that we have to use an iterative method, a self-consistent method. So in a self-consistent method, it's going to work like this. Since I don't know the density to start to calculate this, I'm going to use a guess, an approximation, hopefully good one. Then I'm going to solve this equation and find psi. Now that I have psi, I can calculate the density, right? And I'm going to compare the density to my previous guess, my previous approximation. More than likely, the first step, it will be completely different. I mean, quite different. Hopefully not completely, but quite different. So what do? Well, we have a new approximation for the density. So we put that in the equation and we will calculate psi. Then we have a new approximation for the density and we keep going. So this is what is called a self-consistent loop, and we keep going until the new density we calculate is the same as the one we used to calculate the current psi. So this is what we call a self-consistent equation, which is done iteratively. Now, another concept I would like to talk to you about is effective potential. So we have this really one particle problem here, where we are able to correct the potential, if you will, the attraction of the electron by the ion, by an electron-electron interaction, which is a Hartree term that I just described, right? We can only do that because we imagine that the solution of the full problem is just a product of single particle function. That's what we've done in this entire lecture. Now, we could say that in order to write this in a way that's more typical, which is kinetic energy plus potential, we can say that what in the red box is really an effective potential. So the disadvantage of this is that now in the effective potential, there is both the attraction by the ion and the repulsion from the other electron. Fine, but at least we have something that looks like what is the potential that one given electron effectively feels in being by the system. So this is something we do quite often, and I purposely introduce this effective potential because, again, we are going to see an effective potential slightly different from this one when we go to DFT. So for helium, we saw alpha was equal to 175. 75, if I remember, it was Z minus 1/4. And then, therefore, we can calculate the density as written there, right? So we can calculate, this is basically, what is this? This nx divided by 2 is the Hartree potential divided by 2. So it's the second term of the effective potential. We just said that in the previous slide. So the contribution, of course, is positive. It's a repulsion, electron-electron. So that means that we are going to be able to correct things using now the information we have. So I'm going to show you an example. Of course, here the example is not using Dirac delta, but instead it's using the usual potential. And so we see, for example, here that if the biggest chunk is always going to be the electron-ion interaction. It's in green, which is always negative because the electrons are always attracted to the ions, which are positive because it's a collection of protons and neutrons, but neutrons do not play a role in this case. And of course, we add to the effective potential, we add this electron-electron interaction in blue, which is itself always positive because it's a repulsion. So the effective potential is the sum of the two. And so what the electron actually experience or sees is the red potential. So in other words, it's a little bit like there is the ions and mostly the ion, right? Because the green and the red look very much the same. However, it's not as attractive as the ions were alone. And why is it so? Is because there is a screening of the other electrons. And think about this a little bit. If you were to interact with a positive charge, and now there is a bunch of negative charges that comes around the positive charge, effectively, you would actually not see the full, interact with the full positive charge. You would find, it would be attenuated or screened by the presence of the electron. So this is what we call a screen potential. So the red potential, which is the total, the effective potential, is actually screened potential. It's actually not as strong because of the presence of the electrons nearby. And of course, we can do this for different value of the exponent. For example, if we use like a electron, if we use like a different z, then we can actually start to play with this. Now, I'm going to introduce you something very important to you, and I'm going to talk to you about correlation. Because let's try to take a step. Let's try to pause for a second. What have we done? We have solved basically the two electron problem. we have a good handle on the Pauli exclusion principle. We are good because spin can take care of that. The spins take care of that. We can improve our solution by variational principle. So we have an effective potential that also includes electron-electron interaction. Now it's time to think, when you do this kind of stuff, to remember what's missing. One thing that's fundamentally missing here is the fact that the electrons, the wave function, the trial wave function, is the product of individual particle wave function. So in everything we've done, in particular what I just did in the second part of the screencast, where I just said that the functional is just the sum of the two functional for each independent particle. When I do that, I'm just saying essentially that the approximation I make is that the electrons are independent. And this is, independent when building the trial wave function, essentially, right? Especially, so they do not see explicitly the other one. Now, this is actually the heart of Hartree-Fock. You are missing that chunk. There is no reason why the wave function of a two electron particle can be the product of two single particle. There's no reason why the real answer, the exact answer, is exactly a function where you can separate the two sets of coordinates. But it's a pretty good approximation because individually, each of those single particle solutions are true solution of the problem without the electron-electron interaction. This is why Hartree-Fock was developed, because we can actually start from intuition from the independent particles. However, we are missing definitely energy. And that energy we are missing is called correlation energy. So in Hartree-Fock, this is one of the simplest definitions in the quantum chemistry world. Correlation is what? Is the mistake you make. So it's the difference between the exact energy and the energy you calculate with the method I just told you. And I'm going to repeat it because it's central. The approximation we make is that we posit that the trial wave function is just a product of single particle wave function. That's the approximation we make. In next lecture, I will introduce you, I will show you a parallel between this and probabilities. And hopefully that will give you even more understanding of what's happening here. I should also tell you that density functional theory does not have that problem. It does have other problems, but it does not have that problem. And just to make things a little bit more complicated for you, what we call the correlation energy in DFT is not the same definition as in Hartree-Fock. But let's do one step at a time, if you don't mind. So correlation. The true wave function, of course, satisfies Schrödinger equation and minimizes the ground state energy functional. That we know. So the difference between the Hartree-Fock energy and the exact ground state, as I told you, well, this is what we call the correlation energy. So the correlation energy is indeed what I just told you a minute ago, the difference between the exact solution and the one you calculate. That's it. That's that simple. Now you can calculate the correlation energy, and you see, I'm just giving you some example of hydrogen, helium, and beryllium. We see that those values are actually pretty small, right? These are pretty small, but these are not small enough to be ignored. And in particular, there is a lot of fun physics and interesting property of materials that come from the correlation. People do not do Hartree-Fock typically for looking at solids and materials. They don't do that. They just don't, because the correlation part, especially in metals, but also in other phases of matter, does matter quite a bit. So one thing I'd like to attract your attention on, and it's going to be on the next slide, but I'm using this table here to show you, is that this correlation energy is pretty much the same everywhere, but it's for the three examples, but the total energy goes down pretty fast, which is not surprising, right? Because there is a z square somewhere. So of course the z square, that's why it increases like this. Now, you may, what we are going to do on the next slide is to explain that the correlation is going to be stronger for small values of z. So the portion of correlation compared to the total energy is smaller for smaller value of z. Why is that so? Well, it's actually pretty straightforward, because we saw that the total energy for the Hamiltonian, when we don't put the electron-electron interaction, goes like z square. So the piece that's exact, if you will, goes like z square. The piece that does not, so the piece that goes, that, and at least in the example we showed, the piece that's not exact, so the electron-electron interaction goes like z. So therefore, the proportion of what we don't get right compared to what we get right goes down as z increases, right? That's one point, and I'm going to repeat it again on the next slide. But one thing I'd like to attract your attention to as well, if you look at the energy for helium, which we just tried to solve, and you see it's minus 2.9, and yet we found value of minus 3.06. Well, remember, helium is not a one-dimensional object. In our case, we solve it as one-dimensional. It turns out that it's not one-dimensional, so it's not exactly the same problem as we are doing here. Okay, more on correlation. So we know that the relative importance of correlation changes for different value of z, and I just explained that to you on the previous slide. But what's interesting is that for larger z, the external potential dominates. That's what I just showed you because of the z square, and so the non-interacting solution becomes much more accurate. So that's actually interesting to see that. And again, I'm just going to show you again this slide, the table from previous slide right here. The error we make, the correlation, is 0.004 over 13.6 for beryllium plus plus, while it's 10% for H minus, for example. That's what we mean by that. So of course, as Z is reduced, the interaction becomes more important relative to the external energy. Okay, and so in other words, for large enough Z values, the Hartree and exchange dominate over correlation. And we know that in Hartree-Fock, we get both the Hartree energy, so the electron-electron interaction in a mean field, if you will, and we get the exchange exact. We get the exact exchange. Why? Because our wave function in Hartree-Fock is indeed anti-symmetric. So we obey this Pauli principle, which tells you something about what happens to the wave function when we exchange particles. That's what we need by the exchange energy. So thank you very much. Next time, we are going to do Hartree-Fock theory, and we are going to get a promotion to many electrons. Thank you.